Okay, so today we're going to continue with our unit on bonding, talking about Lewis structures. So Lewis structures show how the valence electrons are arranged among atoms in a molecule. So remember, we're only talking about valence electrons here, which are the outside electrons, and we can find those based on the group numbers. So for each group, we're going to have the same number of valence electrons. Most important requirement for formation of a stable compound is that atoms achieve noble gas electron configuration. So we talked about this before, where elements will either share or steal electrons in order to achieve that noble gas electron configuration. So if we look at, for example, the compound potassium bromide. Potassium, the ion, so K+, has no valence electrons and has donated its one valence electron, and the bromine ion is a negatively charged ion, and it has 8 valence electrons because it took the one from potassium, and so now they are both stable, and so they will form a compound. So let's look at Lewis structures for covalent bonds. So hydrogen follows what's called the duet rule. So it will form two stable molecules when it shares 2 electrons. And so if we have the molecule H2, these 2 dots mean that they are sharing between. We can also turn the pair into a line. And so 2 electrons are being shared between both hydrogens. Okay, if we look at helium, helium is a noble gas. It doesn't form bonds. It already has 2 valence electrons, so it's already stable. And now let's move to the second row nonmetals, which would be boron to neon, or, well, boron technically falls into the metal category, so we're going to look at carbon to fluorine, since neon is a noble gas. These all follow what's called the octet rule, which means they're surrounded by 8 electrons in order to be considered stable. So if we have the compound F2, well, we know based on the periodic table that this is group 1, 2, 3, 4, 5, 6, 7, and so 7 times 2 gives us 14 electrons. They are each surrounded by 8 electrons, okay, 2 being shared, 3 what are called lone pairs, so 1 bonding pair, 3 lone pairs, and so that forms a stable compound. So basically today we're going to talk about how to draw those Lewis structures. If we look at neon, it's a noble gas, it doesn't form bonds. So remember, only valence electrons get represented in the Lewis structure. So let's look at some steps for writing Lewis structures. We're going to sum up the valence electrons for all the atoms in the molecule. Remember, using those group numbers. We use a pair of electrons to form a bond between each pair of bound atoms. So remember, we took that pair and we turned it into a straight line representing a shared pair of electrons. Then we arrange the remaining electrons to satisfy either the duet rule for hydrogen or the octet rule for the second row elements. And we'll talk about elements below the second row in a little bit. So let's look at an example. So we've got H2O, or water. Well, hydrogen is in group 1, so we know it contributes 1 valence electron. Because there are 2 of them, we're going to multiply it by 2, and so we get 2 times 1 plus oxygen's electrons, which are 1 times 1, 2, 3, 4, 5. Ooh, I see a mistake. That shouldn't be an 8. That should be a 6. And so we have 2 plus 6, giving us 8 electrons total. And when we put that together, we put the oxygen in the center. You're always trying to find your central atom, or maybe the one where you can put all your other elements around it. And so we do our hydrogen and our hydrogen. Now that hydrogen is sharing 1 pair, hydrogen is stable, we've used up 2, 4. So I'm going to do lone pair for oxygen, another lone pair for oxygen. So now we have 2, 4, 6, 8. We've used up our 8 electrons, and we've got lines for the shared pairs. Let's look at CO2. We know carbon is in group 4, and so it's going to donate 4 valence electrons. Oxygen donates 6, but there's 2 of them. So we have 12 plus 4 giving us 16. Oops. Okay, and so if we find our center atom, which should be carbon. Now I like to do single bonds on everything first and make sure that my duet and octet rules are satisfied. Then I count and compare to the total I have available. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have too many. So I'm going to take this pair, and instead of carbon and oxygen having their own, I'm going to have them share 1. And so now I have 2, 4, 6, 8, 10, 12, 14, 16, 18. Again, I need to, share another pair. So I'm going to take that pair from oxygen and that pair from carbon, and I'm going to have them share one pair instead. So now I have 2, 4, 6, 8, 10, 12, 14, 16, and so my Lewis structure is correct. Let's just redraw it so it looks a little nicer. And so for carbon, I have 2 double bonds, but that still represents 8 electrons. And for each oxygen, I have a double bond and 2 lone pairs, and so it still also has 8. Okay, let's look at something that's an ion. So cyanide, carbon, we know, donates 4. Nitrogen is in group 5, it donates 5, and then we have this -1. Well, that represents an extra electron, and since we're counting up electrons, we're going to multiply it by 1, and so that gives us 4 plus 5 plus 1, which makes 10. And so now we only have 2 elements here, so we're just going to put them together. I'm just going to give everything lone pairs first, and I also know that because this is an ion, it needs brackets and the charge. So if I count up, I have 2, 4, 6, 8, 10, 12, 14. Again, too many. I'm going to take a pair away from each one and have them share instead. 2, 4, 6, 8, 10, 12. Still too many. I'm going to take another pair away from each and make them share a third pair. And now I have 2, 4, 6, 8, 10. And so I get a triple bond with each of them having their own lone pair and then brackets with the charge. Okay, so we've already gone through 3 examples on how to write Lewis structures. So try these on your own, and then we'll go over them in class. So we've got a periodic table there. You can go ahead and pause and go through those. Okay, so let's look at some exceptions to the octet rule. So boron is an exception. Tends to form compounds in which the boron atom has fewer than 8 electrons. In fact, usually you will see it with 6 electron pairs, sometimes even just 4. And so if those are shared bonds, you would either see 3 bonds or sometimes 2. And so it's not always going to have 4. So for example, boron trifluoride has 24 electrons because we know boron comes from group 3, fluorine comes from group 7. So that's 3 plus 3 times 7, which gives us 24. And if we go ahead and draw that Lewis structure, give everything single bonds. Okay, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So it's satisfied, and boron only has 6 electrons around it, not 8. But since boron is an exception, we know that that's okay. We could form a double bond between the boron and one of the fluorines, but it doesn't need to have 8. So it's one of those exceptions, and even when we form that double bond, it still behaves as though it is electron deficient. Okay, so we said we were going to go down to the period 3 elements. We looked at the period 2, which satisfy the octet rule. Now let's look at period 3. Well, period 3 would start with sodium, and really we're going to mainly be looking at nonmetals. Okay, they can exceed the octet rule. So if we look at something like SF6, it has 48 valence electrons, and so its center atom can exceed that octet rule. Sulfur is going to end up having 12 electrons around it. So we have sulfur and then our 6 fluorines, and since sulfur is our central atom, there's really nowhere else for these fluorines to go, and since sulfur can accommodate more than 8 valence electrons, this works out. And so each of our fluorines is going to have 3 lone pairs, or counting up to 6. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. It's a lot of electrons, but sulfur can handle all of them. And this is mainly due to the fact that the 3d orbital is empty, and so it can accommodate more electrons. Remember how we talked about 4s being, it's got the larger quantum number than 3d, and d will take some electrons, especially to make the shell half full. Well, that's kind of what's going on here, but since that 3d is empty, we can add more electrons in there. Okay, so a few things about the octet rule. Remember, the second row elements, carbon, nitrogen, oxygen, and fluorine, will always obey the octet rule. And second row elements, boron and beryllium, often will have fewer than 8 electrons around them in their compounds, which means that they're very reactive, so they will react with other things. Second row elements never exceed the octet rule since their valence orbitals, the 2s and the 2p, can only accommodate 8 electrons. It's once we get into the 3s that we have that 3d where we can accommodate more electrons. So the third row and heavier often will satisfy the octet rule. So most of the time, we're just going to follow the regular rules. But sometimes they can exceed it by using their empty 3d orbitals like the SF6 compound that we talked about. When writing the Lewis structure for a molecule, satisfy the octet rule for the atoms first. And then if electrons remain after the octet rule has been satisfied, place them on elements having available d orbitals. That is usually going to be the central atom, but make sure that your atom is a period 3 and beyond, because that means it would have an available d orbital. So any extras would go on those. Okay, let's look at some other Lewis structures, mainly for exceptions. So let's look at PCl5. So phosphorus is in group 1, 2, 3, 4, 5. So we have 5 plus 5 times, and chlorine is in group 7. So that gives us 40 electrons. And so we have our phosphorus, chlorine, 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 and chlorine. So right away, we've already exceeded the octet rule. But if we check, phosphorus is a period 3 or below, and so it can accommodate more than 8 electrons. And then we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. And so this is an exception, but because phosphorus is a third period and below, it's okay. Okay, ClF3 is going to behave somewhat similarly. So we have chlorine, which has 7 valence electrons, plus 3 times fluorine, which also has 7. And so this is going to give us 28 electrons. And let's put the rest in here so I don't write over the top of them. Okay, here we go. Okay, so then we have our chlorine, a fluorine, a fluorine, and a fluorine. And now let's go 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, and 28. So now chlorine has exceeded the octet rule. It's got 5 pairs total, 3 of which are bonded pairs, and 2 of which are lone pairs. So if we look at the next one, radon and chlorine, C is a noble gas, so it's got 8 plus 7 times 2, so that's 14, let's see, 22. And so Rn, Cl, Cl, let's do all of our lone pairs. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Now everything has its octet rule satisfied, but we know we have a total of 22 to work with, so I'm going to add an extra pair onto radon, and so it's got 3 lone pairs and 2 bonded pairs. So let's look at our last one. We have iodine and 4 chlorines. Iodine is in group 7, so is chlorine. And then we've got this -1 ion, so we're going to add one more. Now, let's say if this was a positive ion. Because we're counting up electrons, a positive would indicate that we lost an electron. And so instead of adding one, we would be subtracting one. So keep that in mind for any cations or positive ions. All right, so we have, let's see, 7 times 5 basically, plus another one, so that gives us 36. Iodine looks like it's going to be our central atom. And then we'll place 4 chlorines around it. First thing we want to do is satisfy the octet rule for everything. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. I'm short, so I need 34 and 36. So in this case, iodine is way below period 3. It can accommodate more than 8. It's got 4 bonded pairs plus another 2 lone pairs. Okay, so here are the checks for understanding for section 4, Lewis structures. Number 1, what is the most important requirement for the formation of a stable compound? Number 2, what is the difference between the duet rule and the octet rule, and when do each apply? Number 3, summarize the steps for writing Lewis structures. Number 4, write Lewis structures for each of the following. So we have hydrofluoric acid, ammonia, methane or CH4, and nitrogen monoxide, the ion. And number 5, what are the 2 main exceptions to the octet rule? Okay, so give these a try. We'll discuss them in class. Have a good day.